Hello and welcome to the defense of my PhD thesis, xLSTM, Recurrent Neural Network Architectures for Scalable and Efficient Large Language Models. This thesis was supervised by Professor Sepp Hochreiter and Professor Günter Klammbauer. And I'm very happy that Professor Gerhard Neumann from KIT accepted to serve as an external reviewer for this thesis. So now let's start. As we're all experiencing it every day, language models are transforming our world. They have a major impact in across various domains ranging from education to arts and media, marketing, finance, and also especially software development. Software development is the domain where large language models at the moment probably have the highest economic impact, and also this is the domain where they have rapidly evolved from just assistive developer tools like code completion to full autonomous software development agents that can build complete software products on their own without any intervention. And this increase in capability has led to the development of AI research agent, where the LLM acting as an agent not only codes the experiment, instead it proposes the experiments, it runs the experiments, analyzes the results, and eventually at the end even writes a research paper or a report about the experiments. But apart from these special domains, large language models also have a high impact on our daily lives. As chatbots, we communicate every day with the large language model and asking it for information or manage our everyday tasks. In the future, or also even today, LLMs will become more and more our personal assistants or personal agents, where they have access to our email inbox, to our calendar, or they can even book flights or buy items in the internet in our names. And the drawback of all of this is that to serve all these requests stemming from the different domains, the applications, the chatbots, and the personal assistants and the language model agents needs a lot of energy. For example, Google estimates that a median Gemini text prompt uses roughly the energy of watching 9 seconds of TV. And here, voice or image prompts consume even more energy. And what is not yet included here in this calculation are the training energy costs. And these are rapidly evolving and increasing from model generation to model generation. So what this rapid adoption and increasing autonomy of LLM and LLM agent means, it means that the compute and energy efficient architectures are essential for the future development and application of these large language models. And this is exactly the topic that my PhD deals with: compute and energy efficient language model architectures. But before we dive into that, what are actually large language models? So, large language models are neural networks based on the transformer architecture. Language models process text as a sequence of tokens, where each token represents a short word or a few characters. And I have illustrated this here at the bottom. So, for example, let's say that the model gets as text to read R and Ns are doing. Here, these are 3 tokens represented by these embedding vectors. And what the model then outputs, it computes the probability of the next possible tokens. Here, for example, it could be great, good, or bad. And of course, in this case, great, it has the highest probability. And then to generate text, this produced token will then be fed again into the model, and the next token will be predicted. And at the core of these language models is the transformer architecture. And what this transformer architecture does, it transforms these token embedding vectors in a stack or a sequence of transformer blocks. And at the lower level, each transformer block consists of 2 transformation components. The first being the channel mix component, often called also feed-forward layer or MLP, which transforms each token embedding vector individually. In contrast, the sequence mix component mixes the information along the sequence. And especially this sequence mix component is important when we process long documents, because how much computation is put into this sequence determines the overall compute efficiency of the models for very long sequences. And this is exactly the topic of my PhD thesis. So my thesis deals with the sequence mix part of the transformer architecture. In standard transformers, the core component or the core sequence mixing mechanism is the attention mechanism. How does attention work? Attention compares every input to all previous input. So just let's revisit the previous example RNNs are doing. If we want to produce the grade token, transformers compare the doing token to all the previous inputs. Then they produce the grade, and then it's fed in again, and we again compare to all the previous tokens. And this mechanism has been shown to have very good performance on language modeling. And since we can compute this pairwise interaction, this is also very efficient during training, because we can compute all this pairwise interaction in parallel. However, the drawback is that since we have to compare to all the previous inputs, we need to store all of them. That means that the longer the sequence get, the more memory we need to store all the previous inputs. In addition, since we compare to all previous inputs, the compute cost scales quadratically with sequence length. In contrast, there's another fundamental primitive that has a different scaling property. And this is recurrent neural networks, which have been introduced in the 1980s and 1990s. And instead of comparing all the inputs to all the previous inputs, RNNs maintain a fixed memory, which is updated for every new input. So here in the case of this example, at this point, the RNN updates the fixed memory and produces the next token. And then again, it updates the memory again and produces again the next token. And since this fixed state, fixed memory is independent of the sequence length, the memory costs are not growing with the sequence length. So it has a fixed memory. And since the update cost for the memory is constant per step, the overall compute cost scales only linear with the sequence length. This is very cool. However, when we compare it in language modeling performance, it has been shown that these traditional recurrent neural networks perform worse than attention. And in addition, since we have to do this step-by-step updates, the training is not as efficient as transformers because it's not parallelizable. And this is mainly due to how GPUs nowadays work. They prefer highly parallel computations. So this tension between the theoretically better scaling and the practical limitations brings us to the core research question of this thesis. Can we design architectures with transformer quality and RNN efficiency, namely the fixed memory state size in combination with the linear compute cost scaling with sequence length? And towards answering this question, this thesis makes contributions across three axes. The first being novel recurrent architectures, where we propose the xLSTM family. The second are hardware-aware algorithms design, where we design efficient implementations for the xLSTM and general linear ends. And finally, large-scale evaluations of the xLSTM, building a 7 billion parameter model and analyzing scaling laws. But how this all started was with the original LSTM architecture. And the LSTM was initially introduced by Sepp Hochreiter in the 1990s. And the LSTM was introduced to overcome the vanishing gradient problem of traditional RNNs through gating. So gating is the core component of LSTMs. And before the introduction of transformers, LSTM was one of the main methods for sequence and language modeling. And here on the slide, I show the memory update rule for the LSTM architecture. And we see the MLSTM consists of memory, states, the C and the H, and also three gates. And these three gates are the distinctive factor of LSTMs. They consist of a forget gate, here F, an input gate, and an output gate. The input gate controls what goes into the memory, the forget gate what is forgotten, and the output what is output to the next layer. And here, every gate and also the input depends on the current layer input, the X, and also on the previous LSTM output, the previous hidden state, via these recurrent weights. And note, these recurrent weights are very important because important to remember, because these recurrent weights prohibit this sequence parallel training, which is this main advantage of attention over LSTM. So now, as we know how the LSTM works, we started in our research with the initial question, how far do we get in scaling the LSTM to billions of parameters when applying some modern tricks of the trade of language modeling to it? And we found that even though we have used these tricks of modern transformer architectures, we do not get so far with the original LSTM. And the reason for this is that the original LSTM has three main limitations. The first being the inability to revise storage decision. The second being the limited storage capacity. So in comparison to this growing memory of the attention mechanism, the fixed state, which is only a vector in the original LSTM, is just limited and is not enough to store all the facts that are occurring in language modeling. And finally, I've already hinted at it, is the lack of parallelizability, so the inefficient implementations for training. And to overcome this limitation, the xLSTM extends the original LSTM by three novel innovations. The first being the exponential gating. And the exponential gating should improve the information routing into and out of the memory cell state, and therefore overcomes this inability to revise storage decision. The second addition is moving from this limited vector memory to a matrix memory, which is much larger and can store much more facts. And finally, to overcome this parallelization issue, the xLSTM introduces a fully parallelizable xLSTM variant and also improves this old way of memory mixing by making it more efficient. So exponential gating is the core innovation of the xLSTM. So what is exponential gating? Exponential gating enhances the LSTM gating mechanism. It still keeps the forget input and output gates in place, but it modifies the input gate to be an exponential activation function. Remember earlier, the forget input and output gate are all sigmoid activation functions. And now the main difference between the sigmoid input gate and the exponential input gate is that the exponential input gate is unbounded. Sigmoid is bounded to 1 and exponential input gate is unbounded. So now the main idea behind this is that now if there's a new important input, the exponential input gate could amplify this important input. And while the previous sigmoid input gate could maximally multiply this input by 1, so it cannot really amplify it. And in contrast, it must rely on the forget gate mechanism to forget everything. So what this enables is basically that as there is an important input, through this amplification, the input gate allows to overwrite the memory content instead of relying only on a forgetting mechanism. And this enables a more flexible information routing. One can also think of this as that since we have this additional normalizer state, so we normalize the cell state after we have updated it, this is also sort of like a relative state update. So if we amplify the input after this normalization, the current input is kept at a higher, is more prominently represented in the memory state. So this is the high level intuition of exponential gating. So with this exponential gating, the xLSTM introduces two new memory cells, with the first being the sLSTM, which has a scalar cell state. It is a nonlinear RNN, so it still has these recurrent weights that I initially introduced for the original LSTM. So in that sense, it's similar to the original LSTM. And therefore, because of these recurrent weights, it allows memory mixing and is more expressive and enables the so-called state tracking capability. On the other hand, we introduced the mLSTM, where the distinctive property of the mLSTM over the sLSTM is the matrix cell state. This is why mLSTM. So here the cell state is now a matrix, which is larger than the vector or the scalar cells. Typically, the scalar cells are stacked, so they are a vector. This is a linear RNN, so it does not have any recurrent weights anymore, and therefore and it is more efficient and enables this parallel training just as Transformer does. So with these two architectures, we build a language model consisting of Transformer prenorm blocks with the S and mLSTM sequence mixing operation. We stack these M and sLSTM blocks at a certain ratio and compare their performance in language modeling. We compare in our experiments to back then recent competitors like RWKV4 and Mamba2, which are both linear RNNs, so RNNs, and the transformer architecture here indicated as Llama. And we train models ranging from 100 to 1.4 billion parameters on 300 billion tokens from the internet. And we see that across all model sizes, the xLSTM performs best of all models. And here we even train two variants. The first being a variant where we have MLSTM and SLSTM mixed. We have 7 MLSTM per 1 SLSTM block, and the second being only MLSTM blocks. So this leaves us with the question, what layers should we choose for which application? We see here that in our experiments that SLSTM enhances the performance on these so-called state tracking tasks. These are typically synthetic tasks where the model needs to track a state changes over a sequence of inputs. But we haven't seen gains in general language modeling, as we also already see in this experiment. We see that MLSTM is just enough or gives even slightly better performance. However, SLSTM has performed better on other tasks, such as biological and chemical sequence modeling, and especially in time series modeling, where we attribute this performance gains over MLSTM to this enhanced state tracking capability. In contrast, on language modeling, as we see here, MLSTM performs best and is also used for vision LSTM. Therefore, for the remainder of this talk, we focus on the MLSTM. So when we published the paper, our initial question we didn't want to stop at this here. So we trained models up to 1.4 billion and wanted to know how does this trend continue? Because nowadays state-of-the-art models are much, much larger than this 1.4 billion parameters. So this is a very small size. And we actually wanted to do that, but to train larger models, what is necessary are hardware efficient implementations of the new sequence mixing primitives. And these where we did not have these initially. Therefore, the second contribution of this thesis is devoted to this hardware-aware algorithm design, where we propose efficient implementations for the xLSTM with matrix memory, so the MLSTM, and in general linear RNNs. So here, let's revisit how we have introduced the MLSTM. We have introduced the MLSTM with this recurrent update rule, where we have the matrix cell state. And here, this matrix cell state, if this T is basically the sequence of inputs, is computed for every time step. Just as we introduced RNNs, it's the recurrent mode of operation for RNNs. So we materialize the C state, we compute it in every time step, and then we compute the output. This is linear and compute, but not sequence parallel. It's the same problem with the original traditional RNNs. In contrast, since this is a linear RNN, so it doesn't have this recurrent weights, we can parallelize the computation. So we can rearrange this, we can basically change the order of matrix multiplies and completely avoid computing any intermediate states, and then directly compute the output. The disadvantage of this is that this is still quadratic, or this is now quadratic, because we here have a matrix, the Q times KT, which is a quadratic matrix, and it's actually very similar to softmax attention. The main difference here is that softmax attention here still has the softmax at this position. So the drawback is that it is quadratic, even though it's now sequence parallel. So the question is, can we do better? And the answer is yes. There is another formulation which is exactly in between this recurrent formulation and the parallel formulation. And this is called chunkwise parallel formulation. And here the main idea is that instead of materializing the C state at every step, or instead of materializing no C state at all, we materialize every Lth time step a C step. And this L is, for example, the chunk size. And the advantage of this is that overall, like over the chunks, the compute scales still linearly, and we can also parallelize the computation. Within the chunk, we can compute these outputs in parallel, and we can also compute every chunk in parallel to the others. And there exist already efficient implementations for linear RNNs that leverage especially this chunkwise parallel formulation and show that with these kernels, they are already faster than attention. And here, the main property of this, or the main parameter of this chunkwise parallel formulation is the chunk size. And this chunk size determines the number of stored and loaded memory states. We see here, the larger the chunk size, the fewer states we materialize, we compute, and the smaller, the more we materialize. Now, to understand the problem with this original FLA kernels, or the first FLA kernels, we have to understand how GPU works at a high level. So we see here a GPU has as a main component the large memory and multiple small processors which do the computation. And the data transfer between them is very slow, and we need to know that. Now, as a kernel developer, the main task is to keep all these tiny little processing units busy. So we need to parallelize the computation to keep every SM busy here. And now every streaming multiprocessor also has another small intermediate cache where we store, or where we have to load the parts that this SM deals with. And for the case of FLA, these parts are the inputs and the outputs. And now, since FLA loads all the inputs and the outputs direct for one chunk directly in the SRAM, this SRAM size directly limits the chunk size. Note that when we have a small chunk size, we need to store many C states within this slow HBM, and we need to transfer many C states between these streaming multiprocessors and the HBM. And this hinders full utilization of the GPU. And to overcome this, the main idea I came up in tiled flash linear attention was to introduce an additional tiling dimension. Now, instead of fitting all the inputs and outputs per chunk into SRAM, we only fit the inputs and outputs per tile into SRAM. And then we can use as many tiles as we want to decouple the chunk size from the physical SRAM size. And what this enables is that it enables the trade-off between the memory and the runtime. The larger the chunk size, the more quadratic compute we have, because within the chunks, the compute is still quadratic, but overall it's linear. So, and the larger the chunk size, the fewer memory states we have to materialize, which leads to a fewer GPU memory consumption. On the other hand, when we benchmark our tiled flash linear MLSTM kernels, linear attention MLSTM kernels, we see that TFLA reaches state-of-the-art training kernel runtimes. So TFLA kernels are faster than flash attention, which are the blue lines here, and they are also up to 2 times faster than Mamba kernels. With this now fast kernels, this enables large-scale evaluation of xLSTM. And recall, so far we have trained xLSTM models up to 1.4 billion parameters. So the question that we had initially was, does this trend continue? And therefore, we stand for the problem of how to scale the xLSTM to 7 billion parameters and beyond. And we tried a naive scaling where we just use the same code and configure it to be larger and start the training. But however, we observed many training instabilities, and we also observed that the training speeds were very low with this, even though we have this linear scaling with these initial training runs. So what xLSTM 7b is about the optimization of the xLSTM architecture for stable convergence, because we don't want to have these training instabilities occurring halfway through the run and we have to restart from scratch, because this would waste many compute. So we find many tricks here to make this convergence stable by introducing gate soft capping, improved normalization techniques, and also improved initializations. And the second optimization is the optimization for high efficiency during training and inference. And we already have seen how we did that on the kernel level, but we also optimized the architecture on the block level. And for that, we mainly move away from this transformer style block where the channel mix is sort of interleaved with the sequence mix component to the default transformer style block where we have the channel mix separated from the sequence mix component. And the sequence mix component in the xLSTM 7b is the pure MLSTM operation. And with this block architecture change, we achieve a speed up of 2 to 3x at only a slight trade-off in validation perplexity. After this change, we were able to efficiently train xLSTM with 7 billion parameters on 2.3 trillion tokens from the internet, so internet text data. And we used an 8 sequences of 8,000 token length. We trained it on 256 H100 within 12 days. And the final model was on par, or is on par with comparable models on downstream tasks. So here we show models with similar training data set size, and we compare it on MMLU Pro, which measures the general knowledge of the language model. So this architecture now is stable, it trains very efficiently, and therefore can serve as the basis for our final scaling law analysis that compares transformers and xLSTM more thoroughly during training. But before we dive into the results here, let's have a look at what neural scaling laws are actually. So neural scaling laws are an empirical relation between loss, compute, model, or dataset size. And it has been shown that these relations follow power law trends and often hold over many orders of magnitude. And this has significant practical implications. So what scaling laws are typically used for are the prediction of the outcome and also thereby de-risking very large training runs. So this is exemplified here at the picture on the right side. So we use a few training runs with a small compute budget, and then use these the performance of these runs to predict the outcome of one very large run, which is very costly because this run usually takes a month or even longer and requires a lot of compute and energy and also capital investments. What is also possible with the scaling laws, and that's our main interest here in the study, is to compare model classes. So we want to compare transformer with xLSTM. And finally, what scaling laws also allow for is for the compute optimal allocation of model parameters and training tokens. So this, for example, answers the question if someone gives you a cluster or a fixed compute budget. So let's say you have a cluster for 1 month and X GPUs. How big should you choose your model and how big should your dataset size be to get the best performing model out of this fixed compute budget? And this is especially the topic that scaling laws can cover. So in our scaling law study, we basically follow two main approaches that are known from the literature. And here the first approach is the token per parameter approach. So what we do here is we fix the model parameters. So here on this plots, you see on the x-axis the number of training tokens, so the training dataset size, and on the y-axis the model parameters. So what we do is we fix a few sizes, a few models, and then train each model for varying dataset sizes. And then with this study, we can study the loss versus the compute behavior of these models. So what we do then, when we have the outcome of these runs, we fit the loss as a power law in the model and the parameters of the tokens. And this parametric fit function looks as follows here, where n are the model size and d is the dataset size. And we see the fits here of these of our runs here in the right hand side. And in this plot here, we can see the outcome of this first token per parameter and fit approach. So on the x-axis, we plot the compute, where on the left is basically fewer compute, and on the right is more compute. So on the left, it's cheaper. And on the y-axis, we show the validation loss, where lower is better. And what we see here when we look at the Pareto front is that xLSTMs are Pareto dominant to transformers in terms of loss versus compute in our setting here. This is a significant result because it means that we can always obtain one xLSTM with the same quality of transformers, but use fewer compute. Or on the other hand, if we have a fixed compute, there's always one xLSTM that has a lower loss. The second approach that we use in our scaling law study is the isoflop approach. This is exactly the approach which you would use to determine how you choose your token budget and your model size when you have this fixed compute budget. Because what we do is we fix the compute budget and then vary the model parameters and training tokens. And now we can easily see that we have these straight lines in this model parameter per training token plane. And what we study with this experiment is the compute optimal model sizes and the context length dependence of the compute optimal model sizes, which is something that has been ignored or neglected by previous work. And the main results of these isoflop experiments are that the xLSTM attains lower loss for the same compute budget, so similar result as in the loss versus compute regime. then we find that when we have this fixed compute budget, the compute optimal xLSTM model size is larger than transformers. And finally, when we do this ablation on the context length, we find that the compute optimal model sizes remain stable across context length, while the compute optimal model sizes for transformers decreases. And the reason for this is that transformers, when the context lengths get longer, need to allocate a lot of flops into the sequence mix operation and into a tension operation, which scales quadratically. So finally, what is left is the inference speed. And we compare prefill in time to first token. So how long does it take for the model to read a document and answer with the first token? And secondly, how fast can the model generate new text? And for that, I'll show you the results of our xLSTM 7b study, where we measure the inference speeds with batch size 1, which is basically a single user setting when you download the model and run it on your laptop. And here on the left, we see the prefill performance, which is how fast can the model read a code base or read a document, and then answer with the first token. And we see here that the transformer scales quadratically with the sequence length, while the other, like Mamba, is an RNN, scales linearly. And out of these RNNs, xLSTM has the fastest prefill time. Same for generation. Here we measure now the tokens per second, and we see that as the prefill length, so the document, the prompt before the model answers, is longer, the transformer tokens per second is reduced, while the RNNs remain independent of the prefill length. And here we see that xLSTM is even faster than transformer for long and for short prefill length. So we see xLSTM is the fastest model in prefill and generation in our study. So this brings us to the question, why doesn't everybody train xLSTMs or other linear RNNs? And the main reason for this is the main limitation of xLSTM is that the long context performance of xLSTM lags behind the transformers. And to understand this here, I show a result of our xLSTM 7b paper where we measure the long context performance on so-called needle in a haystack tasks, where the model basically needs to recall a magic number out of a long document. And we see that the xLSTM 7b, which was trained on 8,000 token here, this left bar, has decent or very good length extrapolation, out of the box length extrapolation capabilities. So it even sometimes answers gives correct answers for context length up to 100K, 130,000 length of 130,000 tokens, but has only seen 8,000 tokens during training. And and then what we try to do is we try to improve the long context performance. We wanted to figure out whether this is a limitation of the fixed state size or just our recipe. So what we did is, as a very simple thing, we continued pre-training for 50,000 steps with a longer context size, like 32K. And we see that this significantly improves the performance across the whole context length that we evaluated. And this hints to the fact that our current recipe does not fully utilize the fixed memory state. But still, we see that when we compare it to transformers, Llama 3 trained by Meta, it still lags behind. And the main limitation of this is, or the main reason for this limitation is the fixed state size, which limits the memory capacity. So what we see here in this experiment is that there exists a trade-off: the memory state size versus long context performance, and also memory state size versus inference speed. Earlier, we have seen that this fixed state size is the reason for this constant generation time, but also it limits the long context performance. So future work could further push this memory versus efficiency frontier through larger memory size, through new hybrid memory designs, for example, or better use of existing memory through improved training and gating techniques. Finally, our studies are limited to models of 7 billion parameters. Current models are much larger, so future work could scale xLSTMs and integrate them with today's very common mixture of experts architectures. Finally, we should strengthen the xLSTM ecosystem, for example, provide first-class support in major inference engines so that everyone can run the xLSTM at home or on their server. And finally, because this is also a requirement, having a fast inference engine, develop xLSTM based reasoning models. And at last, we should also explore other applications and modalities for xLSTM where it could excel. For example, in robotics, when xLSTM is applied on edge devices, and for that, we could probably build vision language action models and run them on directly on local robots. To summarize, this thesis has contributed across the full stack of large language model development. At first, we have introduced a new LLM architecture, the xLSTM, which matches the transformer in language modeling quality and has a constant memory and linear compute scaling with sequence length. On the system side, we propose a TFLA MLSTM kernels for efficient large-scale training. In this thesis, these kernels enable a 7 billion plus parameter xLSTM models and also enable this memory versus runtime trade-off and show state-of-the-art kernel training kernel performance when compared to Mamba and transformer kernels, attention kernels. Finally, in our large-scale training and evaluation of xLSTM, we have found that xLSTM scales favorably in terms of loss compared to transformers and has significantly faster prefill and generation speeds. To conclude, what is left for now is to revisit our initial research question. Can we design architectures with transformer quality and RNN efficiency? And with RNN efficiency, we mean the fixed memory state size and the linear compute scaling compared to this quadratic compute cost of transformers. And the answer is yes. With the xLSTM, we demonstrate that modernized recurrent architectures can serve as competitive and efficient LLM backbones. With that, I'm at the end, and I want to thank all my co-authors and everyone who supported me throughout this PhD journey. Thanks.